In this video, we're going to look at like a demonstration of where the Polygon Angle Sums theorem comes from. So they want us to look at some polygons and draw diagonals, and then look at the number of triangles that are created by drawing the diagonals. So this is what they're talking about. Let's switch over here to this graph paper. So if we look at this quadrilateral here, this is a parallelogram. What I can do is draw a diagonal from Q to A that cuts this figure into two triangles. Now if I look at the angles in each one of these triangles, we've got those angles there. Now if this is a parallelogram, these two angles can be congruent, but we have an angle there, and we have an angle there, and an angle there also. So we can see that between these two triangles, if we sum up all the angle measures, we basically have all the angle measures inside this quadrilateral. And each one of these triangles has 180 degrees worth of interior angle measures. So two 180s makes 360 total degrees. So one diagonal, two triangles, 360 degrees. Let's look at the pentagon. 5 sides. We can draw a diagonal from there to there, and we can draw another one from here to here. So basically we can make 3 triangles with a pentagon, and we've got this angle, this angle, this angle, this angle. Together these make this angle T. We've got this angle here and this angle here. This makes this inside triangle. And then over here we have that other angle at N that's in this right hand triangle, the other part of P, and the other part of E. So we can see that between these 3 triangles, we've got all the angles that add up to P. Here we've got angle E. Here these two give us together angle N. Those two give us T. And then we have angle A. So between these 3 triangles, all the sums of the angles will add up to all the interior angles of this pentagon. So now we have 3 triangles. Each one of these has 180 degrees. 3 times 180 gives us 540 degrees for the measure of the angles inside the pentagon. And then we can go to the hexagon. Let's see, we can see how many triangles we can get out of that. 1, 2, 3. We can get 4 triangles. So 4 times 180 equals 720 degrees. So a hexagon gives us 720 degrees. Okay, so let's go back to the chart. So let's see, let me change colors up. So to fill this in, let's see what we got. So a square, 4 sides, or parallelogram, 4 sides, quadrilateral, 4 sides. You do the diagonal, and you get 2 triangles. And each triangle is 180 degrees. That gives you 360. We did the pentagon. We got 3 triangles. 3 times 180, 540 degrees. Did the hexagon. 1, 2, 3. Got 4 triangles with the hexagon. There were 4 triangles. 4 times 180, another 180 on top of this, gives us 720 degrees. Now we can see a pattern here. Looks like the number of sides, take away 2, and take away 2 gives us the number of triangles that are created, and then that's going to be multiplied by 180 for the number of degrees in each one of the triangles, which gives us the total. So n minus 2 times 180 is the total number of degrees inside a polygon. A heptagon has 7 sides, hexagon 6, pentagon 5, square 4, octagon 8, nonagon is 9, decagon is 10, undecagon is 11, and dodecagon is 12. So let's see what we got pattern-wise. So heptagon, 7 sides. Take away 2 to find the number of triangles that are formed, which is 5. 5 times 180 gives us 900. So a heptagon has 900 inside degrees. Octagon, 8 sides. 8 take away 2 gives us 6 triangles. 6 times 180 gives us 1,080 degrees. Nonagon, 9. That's going to be 7 times 180. It's going to add another 180 onto that. We get 1260. Is that right? At 1260 degrees. Our decagon, 10 sides, gives us 8 triangles. 8 times 180 gives us 1440 degrees. An undecagon, 11 sides, take away 2 gives us 9 sides. 9 times 180 is going to add another 180 onto this. We're going to get 1620. Is that right? 1640. Right, and 80, 1620. 1440, 1540, and another 80. Yeah, 1620. And then the last one we have is dodecagon, which is 12 sides. Take away 2 gives us 10. 10 times 180 is 1800 degrees. And then this pattern continues. If you had 99 sides, you do 99 take away 2, which would be 97 times 180, and that would be the sum of the inside measures. So let's go down here to the questions. See what we got. Okay, look at the number of sides of each shape and compare it to the number of triangles created. What do you notice? Okay, what we're supposed to notice, or what we should have noticed, is that the number of triangles is 2 less than the number of sides. So if sides is n, we have n minus 2 for the number of the triangles that are formed. What pattern did you notice when you're finding the sum in interior angles, sum of interior angles in each shape? The sum goes up by 180 for each additional side. The formula for the sum of the interior angles in a polygon is n minus 2 times 180. Now that you've done this activity, what do you think the n minus 2 represents? Well, it's the number of triangles formed by diagonals from one vertex. What do you think the 180 represents? The number of degrees in each triangle. And how do both parts of the formula help find the sum of the interior angles in a polygon? Well, n minus 2 is the number of triangles that are formed. 180 is the number of degrees. So the number of sides, take away 2 times 180 gives us the degree measure of the interior angles. Polygon interior angles. So we have a formula, the interior angle theorem for polygons, which says that the number of sides minus 2 times 180 gives us the total number of interior angle degrees for a polygon based on the number of sides.